Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AZIM member FOZI. My main number is AA191548. So now I would like to talk about the BJT characteristic that is bipolar junction transistor. So let's start. Okay, so for introduction, BJT is stand for bipolar junction transistors. It is formed from 3 layers of semiconductor materials. Its operations depends on both types of charge carriers, which is holes and electrons. It has 3 electrodes being called the emitter, base and collector. Emitter is heavily doped, base lightly doped, and collector only moderately doped. Base layer is narrow compared to the 2 outer layer, and it is more lightly doped. Okay, so for types of BJT, there's 2 possible devices polarities for BJT. There is NPN and PNP. It is produced to PN junction. So this is a PNP symbol and this is NPN symbol. This is for construction NPN and this is PNP. NPN transistors require a power supply with positive polarity with respect to common terminals, but PNP transistors require a negative power supply. Okay, so for operation, to properly bias the transistor for normal operation in the active region, one junction must be forward biased, while the other junction is reverse biased. So DC biasing is necessary to establish the proper operation for AC amplification. The construction of the device is such that the base region is very thin, allows the base to act as a control input. Signals applied to this electrode can be used to produce and control currents between the other 2 terminals. So each bias condition for PNP transistors will be discussed separately and then the results will combine. So this is the forward bias of emitter base junction. The depletion region at this junction narrows, allowing the holes to diffuse into the base. Okay, so for this is a reverse biasing of collector base junction. The depletion region at this junction widens, inhibiting the flow of majority carriers. However, a limited number of minority carriers, that is holes, will drift through the junction, establishing a reverse current or leakage current. Okay, so for next one is configuration type. The first one is common base. Yeah, that is CB. In a common base mode, which is also called grounded base, the base terminal of the BJT is used as the common terminal for both input and output of the configuration. The input signal is fed across the base and emitter of the BJT, and the resulting output signal is derived across the base and the collector terminals of the BJT. The base signal is always referenced to the emitter terminals and its potential level. Next one is common emitter, that's CE. So in the common emitter or grounded emitter configuration, the input signal is placed across the base and the emitter, while the output is extracted from across the collector and the emitter as demonstrated. This sort of arrangement is one of the widely used circuit for transistor-based amplifier and it signifies the normal approach to bipolar transistor network. The common emitter amplifier construction delivers the very best current and power gain among three bipolar transistor designs. This is largely because the input impedance is small, since it is attached to a forward bias PN junction, while the output impedance is large since it is obtained from a reverse bias PN junction. So this is NPN transistor and this is PNP transistor. The last one is common collector, that is CC. In the common collector, the collector now becomes common reference with regards to the supply. The input signal is hooked up straight to the base, whereas the output is extracted through the emitter load as indicated in the diagram. This kind of arrangement is usually recognized as a voltage follower or emitter follower circuit. The common collector or emitter follower construction is incredibly helpful for impedance matching application due to its extremely high input impedance, approximately thousands of ohms, while featuring a comparatively lower outcome impedance. So this is an example of BJT, that is 2N4401. 2N4401 is actually a current control device where small current at the base side is used to control the large current at the emitter and collector side. When a positive voltage is applied at the base side, it gets biased and allows the current to flow from emitter to collector. So this is the datasheet of 2N4401. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AZIM Ibn KAMIL. Right, today I will present to you about our group project electronic, which is my part, which is JFET, junction gate feedback transistor. First, we go to the JFET introduction. What is JFET? JFET is an abbreviation of junction feedback transistor. JFET is a voltage control device. It has three terminals denoted as gate, drain and source. Jfet is an essential component for precision level voltage operated controls. Jfet acts as a voltage control resistor or as a switch. It is an energy efficient, which has low power consumption and also low power dissipation. It also provides very high input impedance. Right, there are two types of JFET, which is P-channel JFET and N-channel JFET. Current flowing to the drain and source is dependable, which is it depends on the voltage applied on the gate terminal. For P-channel JFET, arrow pointing out from the gate terminal, and for N-channel JFET, arrow pointing in from gate terminal. Right, P-channel gate voltage is positive, but for N-channel gate voltage is negative. Next, we go to the construction of JFET. Right, N-channel JFET consists of P-type material in N-type substrate, but for P-channel JFET, it consists of N-type material in P-type substrate. JFET is constructed using the long channel of semiconductor material, which is if the JFET contains a great number of negative charge carriers, which is electron, it will be N-channel JFET. But if JFET contains a great number of positive charge carriers, which is holes, it will be P-channel JFET. Right, go to the working of JFET. We know that JFET is a unipolar device, which is it depends on the conduction of N or P channel. Current flow can be controlled by varying the voltage applied to the gate. Okay, JFET is a resistive part, which VDS causes a current ID to flow. Voltage gradient is thus formed down the length of the channel, with this voltage becoming less positive as we go from the drain terminal to the source terminal. The result is that the PN junction therefore has a high reverse bias at the drain terminal and lower reverse bias at source terminal. This bias causes the depletion layer to be formed within the channel and whose width increases with the bias. The magnitude of the current flowing to the channel between the drain and source terminal is controlled by a voltage applied to the gate terminal. When a VGS applied in reverse polarity, that makes the PN junction reverse bias and make the channel narrower by increasing the depletion layer, and could put the JFET in cut off or pinch off mode. Right, next we go to the JFET characteristic curve. As you can see, this is the characteristic graph. We have 4 regions, which is ohmic region, saturation region, breakdown region, and also pinch off region. Right, first we go to the ohmic region. What is ohmic region? Ohmic region is when VGS is equal to 0, the depletion layer of the channel is very small, and the JFET acts as like a voltage control resistor. Right, next, pinch off region. VGS is sufficient to cause a JFET to act as an open circuit as the channel resistance is at maximum. Next, we go to breakdown region. The voltage between the drain and the source VDS is high enough to causes the JFET's resistive channel to break down and pass uncontrolled maximum current. And lastly, we have saturation region, where the JFET become a good conductor and is controlled by the gate source voltage VGS, while the drain source voltage VDS has little or no effect. Okay, this is the JFET configuration basic. We have 3 configuration. Okay, first we have common source. The common source circuit provides a medium input and output impedance level. Both current and voltage gain can be described as medium, but the output is the inverse of the input. Okay, which means that the output is 180 degree change from the input. This provides a good overall performance, and as such it is often taught as a most widely used configuration. Okay, next we have common drain. This is the source voltage follows that of the gate, offering a high input impedance and a low output impedance. It is widely used as a buffer. The voltage gain is unity, although current gain is high. The input and output signal are in phase. Next, we have common gate. Provide a low input impedance while offering a high output impedance. Although the voltage is high, the current gain is low, and the overall power gain is also low when compared to the other FET circuit configuration available. The other salient failure of this configuration is that the input and output are in phase. Okay, this is the example of JFET. This is the LSK 389. Okay, what is 389? The LSK 389 series of high performance monolithic dual JFETs features extremely low noise, tight offset voltage, and low drift over temperature specification, and is targeted for use in a wide range of precision instrumentation application. The LSK 389 is the lowest noise junction filter effect transistor JFET in its class and has been used in ultra high end audio application for over a decade. The LSK enables developers to create the lowest noise signal chain possible for sensors, professional audio equipment, and other applications. The LSK 389 is the key to building the world's lowest noise signal chain for many applications. Right, lastly, we have datasheet of LSK 389. Okay, this datasheet is from Linear Integrated System Company. As you can see, it has features and other experiment that I have done on LSK 389. Okay, I think that's all from me. Thank you.
Assalamualaikum. My name is Muhammad Aiman HAIQAL bin Abdul. My number matrix is AA19162. For my part, I will explain about comparison and exercise as amplifier application. Okay, comparison table. Comparison table between BJT and JFET. JFET and BJT. 1. For JFET, it is an bipolar device. Current conduction is only due to one type of majority carrier, either electron or hole. for BJT is it is a bipolar device. Current conditioned by both type of carrier, majority and minority electron and hole. Second, for JFET, the operation depend on the control of a junction depletion with under reverse bias. For BJT, the operation depend on the injection of minority carriers across a forward bias junction. Third, for JFET, voltage-driven device, the current through the two terminal is controlled by a voltage at the third terminal gate. For BJT, current-driven device, the current through the two terminal is controlled by a current at the third terminal base. For the JFET, it is a low noise level, and for BJT is high noise level. 5. For JFET, it is high input impedance due to reverse bias, and for BJT, low input impedance due to forward bias. And next 6, for JFET, gain is characterized by transconductance, and BJT is gain is characterized by voltage gain. And 7, for JFET, better thermal stability, and for BJT, it less thermal stability. Okay, next it is implementation. Okay, implementation. BJT or bipolar junction transistor can be used as an amplifier, filter, rectifier, oscillator, or even a switch. And for JFET are 3-terminal semiconductor device that can be used as electronically controlled switch or resistors or to build amplifier. Unlike bipolar junction transistor, JFETs are exclusive voltage control in that they do not need a biasing current. Next is example of voltage divider biasing circuit. Okay, this is common emitter amplifier for BJT. Next is common source amplifier for JFET. Okay, formula and calculation. This voltage divider circuit of BJT in Proteus. Okay, related formula is Vs equal to R2 over R1 plus R2 times VCC. Next is VE equal to VB minus VBE. Next is IE equal to VE over RE. Next is VCE equal to VCC minus IC equal to RC minus RE. IC is approximately equal to IE. Okay. This is voltage divider circuit of JFET in Proteus. Okay, related formula for JFET is 1. Voltage control device. Use Kirchhoff voltage equation. Negative VR2 minus VGS plus VRS equal to 0. Next is VRS equal to VR2 plus VGS. Next is VRS equal to ID times RS. Next is ID times RS equal to VR2 plus VGS. Next, RS equal to VR2 plus VGS divided by ID. Okay, this is the reference that we use for our presentation. Okay, that's all from me. Thank you.